Hello, everyone. This is Marco Silveira. It's a pleasure to introduce today's speaker, Dr. Bill Peterson. Bill got his PhD in atomic and molecular physics at the University of Colorado. He was introduced to space physics during his second postdoc at Johns Hopkins University. There, Bill worked with John During, Tom Poterma, and the members of the Ionospheric Explorer C, D, and E teams on interpreting data from these groundbreaking series of satellites. Bill then joined Ed Shelley and the team at the Lockheed Palo Alto Research Laboratories, interpreting data from a series of energetic ion mass spectrometers that flew on ISEE-1, DE-1, empty, polar, and fast. During downturns in funding, Bill spent sabbaticals at the Canadian National Research Council, where he was introduced to the Akebono data, and at the University of Colorado. Bill retired from Lockheed in 2001, and he has been at the University of Colorado since. He is a co-investigator on MAVEN mission to Mars. He has served as a discipline scientist at NASA. And today, Dr. Bill will talk about ionospheric outflow, observational constraints on global models. So before we begin, I'd like to remind you all that this presentation is being recorded. Please keep your voice on mute. And if you have any questions, please post them in the chat box. For those attending on YouTube, you can find the instructions to send your questions in the video description. So I'll be happy to read all the questions in the end of this presentation. Okay, let's begin. Dr. Bill, please proceed.
Well, thank you, Marcos, and thank you for inviting me. I want to thank my many collaborators that are listed here, particularly Andrew Yao. And I'll tell you that I want to use this opportunity to show how ionospheric outflow can be used to put observational constraints on global models. The outline is a standard outline, and I'll have an introduction and a review, and I'll go through, after I've done that, I'll go through a series of examples. At the end, I'm going to tell you what I don't know but wish I did, and I hope that that inspires somebody to do some more work on this topic, which surely can be continued. So first, to get the big picture in pictures, this is a picture that I purloined from Andrew Yao that shows the ionosphere here, which is the source of outflowing ions at about 500 kilometers, where the plasma goes from collisional to collisionless. The thermal plasma goes up into the polar wind, and it goes up into the plasmasphere. But on auroral field lines, where energy comes in from the magnetosphere, there are weird and wonderful kind of plasma processes that produce these funny things called beams and conics that we'll talk about later. As the ions go up, they are centrifugally accelerated at high altitudes, and they are convected into the tail. And then when they get captured in the plasma sheet, they convect up and hit hundreds of kilometers, hundreds of keV kind of energies. You've heard talks in this series before by Fuselier and Laveau about this process, and it's still the same process. I don't like equations, so let me describe the magnetosphere in words. Most of the energy is in the magnetic field, so that determines the large-scale structure. The solar wind and gravity determine the extent and shape of the magnetosphere. Ions and electrons come from the solar wind and the ionosphere. Ions are heavy and slow, so they define the fine structure. Electrons are light and fast, so they go wherever they want. Electron interactions with ions create plasma waves that transfer energy and momentum between ions, electrons, and the magnetic field and make plasma physicists cheer. Electrons make up almost all of the currents. And finally, energy matters. So we've been playing this game of ion outflow observations or superthermal ion observations since the dawn of the space age back in the early 1960s. So thermal and superthermal, let me define that first. Thermal is where the ions are created in the ionosphere with about a volt of energy, less than 10,000 Kelvin, and superthermal is greater than that. So I'm going to talk today about data from the Canadian ISIS-1 satellite, NASA's DE-1, the Japanese Akebono satellite, NASA's Polar and FAST satellites, the Cluster satellite, Canadian EPOP satellite, DMSP, and at the end I'll be presenting data from the Arrays Japanese satellite, as well as MAVEN, Mars Express, and Venus Express. So we're going to do a tour of 40 years of ion outflow observations. The standard view of ions in the magnetosphere is that there's a zoo of particles, including molecular ions, NO+, and O2+, created by solar EUV, precipitating electrons, and chemistry. The energy from the solar wind drives field-aligned currents in convection and creates plasma waves. Ions are warmed in the ionosphere and driven up to higher altitudes, assisted by ambipolar electric fields. And then in the region between the top of the ionosphere and about 2 Earth radii or 6,000 kilometers, there's a bunch of plasma wave interactions that's called the gap region. The gap region is called that because modelers can't model it very well. We ignore WRMO plus shows up in the cloak region. Rick Chappell later this week will talk in the GEM session about this, so I'm not going to address it here. And we ignore H plus because we can't tell whether it's from the solar wind or the ionosphere. And I'm going to make an estimate to show you how you can use data to ask that. We only think about helium plus when it's in the plasmasphere, and we ignore molecular ions in thermospheric chemistry. And I'm going to argue that perhaps there's a lot to be learned if we don't ignore it and go to the hard work of including it. So before S33, which was launched in the 70s, it was a military satellite at Lockheed that introduced us to energetic ions. The focus was on hydrogen and helium in the polar wind. The ISIS observations by Hoffman were limited by attitude data quality, and the common workaround on those missions was to assume that O+ had a vertical velocity of 0. And that was done because nobody believed that oxygen could get enough energy to escape. Shelley discovered precipitating energetic oxygen when they were looking for precipitating alphas from the magnetosphere. The instrument was only funded to scan up to helium double plus, but he extended the range to go out to oxygen and made the discovery that forced the rest of us to go looking for the sources of energetic oxygen in the magnetosphere. Rick Chappell had an instrument on DE-1, and there wasn't really a lot of data that came from that because they were limited by uncertainties in the spacecraft potential and the trouble that they had to go to run the neutralizer that they had. It wasn't until the 90s that a large volume of upflowing thermal ion data were available, and now I'm going to show them to you. This is a complicated slide, so I'll walk you through it kind of slowly. What we have here is altitude from the surface to 10,000 kilometers, velocity parallel upward and downward from the day side on this side and the night side on that side, of hydrogen, which is given by the circles, helium plus, which is given by the X's, and oxygen, which is given by the pluses as a function of altitude. These are average data. The scatter in the data are quite large, and the scatter is indicated by the plot here, which gives the deviation of each point in velocity as a function of altitude for the various species. The data are also limited by the number of samples, and the number of samples are shown from up here. Escape velocity is 11 kilometers at the surface and decreases with altitude. So I've drawn escape velocity as a function of altitude, showing that at 10,000 kilometers, it's down to about 5 kilometers a second. So we can see that the only ion on the day side, hydrogen, has escape velocity observed, but the other ions are right, well, at the highest altitudes, they're right at escape velocity. These data are from the polar cap. So auroral zone and cusp data, where those pesky plasma waves are energizing plasma, have been excluded from the data. The energy at the top side of the ionosphere to get is given here. Hydrogen is a half a volt at corresponding to 10 kilometers a second. Molecular ions need 16 volts to reach that velocity. So what is the energy at the top side of the gap region at 2RE? Well, it turns out that the polar data, energetic ion mass spectrometer data on polar that I published some time ago, can be used to show that. And what we have here are the flux of ions in the 15 to 33 kilovolt range as a function of magnetic local time for hydrogen, oxygen, and helium for 3 years in the late 90s. These data are presented in boundary normal coordinates. What we've done is we've taken the electron data measured on polar and identified the polar cap boundary and the following how Newell did it, and then the poleward edge of the auroral zone. Now, this distribution shows that the auroral zone has the same thickness at noon and midnight, and that's the lack of my IDL skills. If I was brighter, I could put this in a more realistic distribution where the auroral oval really is thinner on day side than it is on night side. We can see that ion outflow, energetic ion outflow is mostly on auroral field lines. There's not much in the polar cap. It comes from noon and midnight. So a first order wag at how the ion outflow is distributed is, you can say there's a third that comes from noon, a third that comes from midnight, and a third that comes from dawn and dusk. Now, how can we get about addressing the energy of these ions? Well, what we can do is we can take and get a characteristic energy by dividing the energy flux, which isn't shown, by the number flux, and present the values that are shown here. And this shows that oxygen has lower energies on the day side than on the night side, and that's also from hydrogen. And is that characteristic? So this is over the energy range that these data are sampled from 15 to 33 kilovolts. So is this characteristic energy difference real, or is it an artifact of the way the data were collected? And the answer, of course, is maybe. The devil's always in the details. And the first hint we get for this is a paper that was published by Chris Cully as part of his master's thesis back in the 90s, where he compared data from Akebono, upflowing O+ and H+ data from Akebono, DE1, and polar. These data sets, Akebono he limited his data from 6 to 10,000 kilometers and from 0 to 20 volts. DE1 mass spectrometer was taken from 10,000 to 16,000 kilometers, and the energy range is from 10 to 24 kilovolts. The polar data I showed you in the previous slide is taken from 6 to 8,000 kilometers over the energy range 15 to 33 kilovolts. So let's look at what he saw for H+. The polar data, shown in diamonds, take 6 months to acquire, so we can only use the KP that's characteristic of that 6 months, and these are the seasons where the data have been acquired and binned. So if we look at the Akebono data in squares, compare them to the DE, we see that at low activity, that Akebono is seeing more upflowing hydrogen. And at the high activity, it's just the opposite. Now, the way we interpret this is that at low activity, we don't expect hydrogen to be very much energized, and we assume that it isn't energized into the DE energy range, and so we miss it. But at high activity, Akebono misses it. For oxygen, we note that the energy threshold on DE1 is less than the energy threshold on polar, and we note that we have to, it takes 6 months to get the data. We can argue that this might suggest that the oxygen is in slightly lower energies than the hydrogen at polar altitude. When we looked at our paper and the data, we made the assumption that we came to the conclusion that there was very little O+ below 10 volts coming up over the polar cap. And the Akebono data are consistent with this. Remember, this is over the whole polar cap. The data that we were showing before was did not include the auroral zone. So we can go one step further. The tide people on polar, Yijin Su and her colleagues, were able to get polar wind velocity, not as synoptic as the energetic data, but they were able to get polar wind energy in the polar cap at about 9 RE, and provided velocity and densities at that. And so what we could do is we could take the fluxes. There was no magnetic local time distribution here, so we had to take the whole polar cap. But what we could do is we could use these density and velocity values measured on by the tide that goes down to the lowest energies, and compare them to the ones that were measured in the 15 to 33 kilovolt range. And if we look in the auroral zone, we estimated that the TIMUS instrument above 15 volts only saw 3% of the hydrogen, which would give an estimated energy of 30 volts. For oxygen, the same calculation estimated that 40% of the energetic ions observed here were only 40% of what was coming up, and reduced the energy to low. Now, this is a WAG. It's most probably not correct, but the most important thing to derive from this is that there's a significant population of low energy ions at the top of the gap region coming out. So it isn't all energetic ions as much as I would like to, well, this is the way the data are. So let's go into the gap region. So 40 years of observations have established that oxygen and hydrogen are energized, and that most of the energy is provided below 2 RE, although there's evidence that it continues higher, like centrifugal acceleration occurs at higher altitudes. So we also know that most of the ions that are upwelling in the thermal do not reach high altitude. So Rob Redman, as part of his thesis, was looking at energization in the gap region, and what he wanted to do was look at the upwelling ions at DMSP, which are primarily O+, and compare them to the polar and fast data, which were acquired higher. Again, we're talking here in boundary coordinates. This is the poleward boundary, and this is the auroral boundary. And we see that the upwelling is stronger on the night side than it is on the day side, but it's not particularly peaked. Whereas the O+ seen at higher altitudes, it seems to acquire its energy mostly in the middle of the auroral zone, not at the edges, as perhaps some of us had thought. Redmond made this, this plot of efficiency by dividing the O plus fluxes by the DMSP fluxes and got a maximum conversion of 65% for this bin, which looks anomalous. Given that the energy range here and the energy range here are not, there's not much we can conclude from this. In fact, I don't know why I kept this in the talk. So how are ions accelerated and energized? Well, we know they're pushed from the thermosphere and the ionosphere by things called gravity waves and Joule heating, and they get kicks from plasma processes in the gap region on auroral field lines. These processes occur between the plasmasphere and the polar cap. And this is an attempt to name the zoo, characterize the zoo of acceleration processes that occur from the equatorward edge of the auroral zone to the polarward edge of the auroral zone. Energy is coming in as alphane waves. Now, I'm not going to attempt to name all of these animals. In fact, I'm only going to talk about one of these animals, and that is the ion cyclotron resonance heating or turbulence that is listed here. And we'll go on to the next slide. Before I get to the next slide, I need to talk about beams and conics. I've just recently learned that most of my younger colleagues don't have fuzzy pictures of what a beam and a conic is. These are ion distributions that are observed on auroral field lines, and as they go out into the magnetosphere. So a beam is a distribution that's flowing usually along a field line, but it can be flowing, drifting and flowing, where the energy or the temperature perpendicular and parallel to the magnetic fields are roughly comparable and larger than the net drift velocity. That's an ion beam. For a conic, here we have hydrogen here and oxygen here. A conic is where the energy or velocity perpendicular to the magnetic field is less than that parallel to the magnetic field. And these funny shapes have two things. They can be real, or they can be an artifact of the energy resolution of the instrument that's taking them. In this case, I think that the energy resolution was probably poorer here than it was there and resulted in this kind of distribution. So back in the 80s, Tom Chang had a way to describe how these oxygen ions acquire their energy. Here's a conic that was observed on DE1, and what was observed simultaneously from the Iowa wave instrument was the power spectral density of the waves. So what Chang did is he took the power spectral density at the oxygen gyro frequency and developed a relationship where he could determine the heating rate and make a prediction of the shape of the conic. And he did pretty well. But he had one dirty little secret. Well, it wasn't so dirty and it wasn't so little. But he did point out that he had too much power at the wave spectra. So the workaround was to say that only 10% of the wave power had left-hand polarization and actually interacts with the ions. And that was good, and we went with that for a while. But then we had Polar had a burst electric field mode data, and Vasilis Angelopoulos, when he was working at Berkeley, when he first started at Berkeley, had a look at the electric field data and the burst mode data and published a very nice paper where he went in and convincingly demonstrated that there was no power at the ion gyro frequency. That was merely Doppler shifting because the satellite was flying through a density structure, and that was just what was there. But we do know that something was there because there was locally heated O+. You don't get O+ perpendicular to a field line it doesn't stay there very long. If you don't continually add power, the grad B forces it go up the field line and convert into a beam. And so we know that there's a wave there coming from turbulence or other wave modes that heat it. We don't know what those wave modes are, and we aren't going to resolve it until we have ion and electron measurements with the cadence, at least the cadence that we had from FAST, on MMS. So the other way to look at the gap region was suggested by Strangeway, who looked at the FAST data on the day side and parameterized energy in from the alphane waves to ions out, measured on the same satellite. This has recently been updated by Hatch, and maybe some of I have objected to this approach because I think that these processes depend on MLT and the relations that Strangeway got on the day side. I don't think, and I think people agree now, don't apply at all local times. So, but this approach does work, and it had a particularly good success when Brambles and his colleagues were able to take a global model that parameterized power in and out, ion outflow, and was able to provide key insights into seeing how these things called sawtooth oscillations in the geomagnetic tail are formed. That was a good success about 10 years ago. So global models are indeed getting better in the gap region. About 2 or 3 months ago, I was asked to review a paper by Alex Glosser that did just that. And and this is a figure from his paper that can be compared here. I didn't like the fact that this is a linear color bar and this is a logarithmic color bar. So Alex was kind enough to provide me with a color bar that has 3 orders of magnitude and is directly comparable. Well, it's not directly comparable. But before I go to the comparison, let me tell you about what I like about his model. He feeds the gap region with a polar wind model. He doesn't put in molecular ions, but that's a trivial detail, right? Right. And he uses a hybrid PIC model with Monte Carlo collisions on specific field lines, and he follows those field lines as they drift around in the magnetosphere, in the ionosphere. So here is at 2RE, which is comparable to here, dawn and dusk, noon and midnight, dawn and dusk, 75 degrees, and I don't know, 70 degrees. This is geographic coordinates, hydrogen and oxygen. And these are, of course, this is at the peak of a geomagnetic storm. This is data that's acquired over 3 years at quiet times where DST was greater than -50 and in boundary coordinates. But they are, you see that there is outflow at all local times. It does have a peak here. It seems to be shifted more to the Dawnward side than the observations, but this is a good comparison. The differences in data acquisition and we can't say whether taking data like these and averaging a bunch of these data over a bunch of quiet periods would produce this, or if we had a bunch of satellites that could fly over and report ion outflow at local magnetic times would see that. So this is good progress. We're at an impasse between data and models. We need better data and models. So I was pleased to see the results of this model. And there's much more in the paper, and I'll let Glosser, you'll hear from him more about that. So let's do more about testing models. I want to talk about downward biases in O+ outflow, using molecular ions as tracer, and the contribution of solar wind plasma to the magnetosphere. So let's start off by the downward bias in the O+ outflow. The first and most spectacular report of this was by Pollack in 1990 from the Dynamics Explorer RIMS instrument, where he looked at upflowing O+ fluxes. This is a grayscale. This is the gray color bar distribution. It's really bad reproduction. I probably should have gone and hunted for a better one, but I didn't. But it shows that the thermal O+ that was measured by the RIMS instrument on DE1 was peaked at, was shifted to dawn, more so than the IMF BY component would indicate would be possible. Redmond took a look at the Redmond and I took a look at the DE1 ion outflow data and plotted maps, and for KP less than 2, we see a slight shift in the O+ towards dawn. For the fast data, Anderson has fast data in boundary coordinates. These are the auroral zone, these are samples, this is the polar cap over here. These are, shows the ion outflow is peaked slightly towards dawn. The DMSP outflow upwelling is not peaked. It seems to be, has this kind of distribution, and the polar distribution we've shown here is biased towards dawn. So Redmond showed that when he looked through the ionospheric literature, found that the rapid onset of field-aligned upward O+ is associated with sunrise, and it was one of the first results, first radar results from Evans. This is reproduced in flip models, and you can actually see it here if you squint your eyes and read the color bars. But what Redmond ran the flip model in the auroral zone at DMSP latitude. He ran 2 models of the 2 kinds of the flip code, one with a neutral wind model and one naked without. And both of them show this, this peak of about a factor of 2 of intense, more intense outflow near dawn. So the shift is resolved. The source of the O+ peaks shortly, upwelling peaks shortly after dawn. The energy input comes from reconnection, which centers around noon, and the IMF BY component moves that around a little bit, but Redmond in his thesis showed that that was small. So, and the prediction comes that the shift is largest during the quietest time and smallest during the most active times. So there we are. So molecular ions, are they time tags? Can we use simultaneous observations in the ionosphere of thermal molecular ions and in the plasma sheet to put strong constraints on large-scale geomagnetic moments, or how large? So molecular ions are observed with plasma sheet energies up to 100 kilovolts, and how and where and how fast are they acquired? So they've been, molecular ions in the magnetosphere and the plasma sheet have been observed for over 40 years. They've been reported on AMTI, IC, Geotail, Polar, Artemis, and most recently on the Japanese ARRAYS satellite. On the right here, we have a figure from a paper that Seki published last year that shows a 30-minute average of about L of 5 before a small geomagnetic storm and after, and marking where O+ and molecular ions would show, and showing the relatively onset here. So she's looked at data from most of 2017 and plotted it here. What's shown in black are the orbit tracks of the ARRAYS satellite going out to about L of 8. And colored on there are the relative signal intensity as in the path as they go. Now she's taken over here and plotted events and samples, and then the occurrence frequency. And what we see here is that the occurrence frequency at about 5% peaks at L of 5 of these molecular ion detections. As a function of DST, when DST goes below minus 100, they're almost 100% of the time. And for ionospheric conditions, they require a relatively active AL. So what about the ionospheric source? So they've been observed on every satellite that's been able to look at cold plasma and had the mass resolution, ISIS, AEC, DE1, Akebono, Polar, and EPOP. Here's observations from the 1972 geomagnetic storm reported by Hoffman and his colleagues, O2+, N2+, NO+, N+, and of course, O+. The recent EPOP satellite is the most sensitive instrument to molecular ions yet flown. It has an orbit of 500 kilometers to about 1,500 kilometers near polar. And Victoria Fox, Yao's graduate student, has started to put together molecular ion observations. She's characterized the signal strength as low, medium, and high, and showed their location as a function of geographic geographic latitude and magnetic local time. She finds about a 6 to 10% occurrence rate. She finds them both flowing upward and downward. She finds more of them in the pre-midnight sector, and she finds that molecular ions are closely associated with N+. So can we use these as time tags? No, because space is big and they seem to come from all local times. So there's no unique source and there's no unique destination. But if we had multiple CubeSats below 1,500 kilometers at several magnetic local times, we could do that, or we could go back and, or we could create global maps and do the analysis more as a function of local time. Or we could start to plug things in, put molecular ions in models and see if they provide any further insight. So let me start about my last comparison, or my next to last in comparison. How important is the solar wind source? Here's a slide that tells everything you need to know about the solar wind source. The source strength was estimated by Hill in '74. It's mostly hydrogen with a small component of multiple charge state oxygen. And the energy input has been a cottage industry, and people are producing estimates of how much energy comes in to be used in global models. So my colleague Ed Shelley gave an AGU talk in the 80s where he estimated the geogenic and heliogenic plasma in the magnetosphere. This paper never made it to prime time. He never published it. And I put the analysis in a paper that got in a book of papers from substorms that never was widely known. So I'm going to repeat it here. So geogenic means of Earth origin, and that means H+ and O+. And heliogenic, of course, means of solar wind origin. And his analysis is based on the parameterizations of ion outflow as a function of AE and F10.7 that came from DE1 by Yao. And here's the parameterization that was published in the 1988 paper. And the other plasma sheet observations from ICI by Lennartson, when ICI went through the geomagnetic tail in '79 and '78, and he has hydrogen density and oxygen density as a function of AE for these two different levels of of solar activity. So Shelley makes two assumptions. One, that the plasma sheet volume is constant, which is questionable, but that's the assumption. And the other assumption is that the ratio is constant for specific, H plus and O plus outflowing ratios are constant for specific values of geomagnetic activity. And if you put these in and grind the numbers, you get the fraction of the plasma sheet, not the magnetosphere, the plasma sheet, that is of geogenic content as a function of AE and for two levels of F10.7. Now this is 1%, this is 10%, and this is 100%. So Shelley's model predicted that when AE is quiet, on the order of 20, exceptionally quiet times, the geogenic content of the plasma sheet is 2 or 3%. At active times, it predicts that the geogenic content of the plasma sheet is 20 or 30%. This would be a good thing for models to have a wag at, to see if they can see how important the solar wind is in terms of the content, and as a closure between to tie in the solar wind observations with the ionospheric outflow observations. So the last thing I'm going to mention is out of this world. I'm a participant, as are various other people in this community, and LASP is the host of one of the NASA Drive Science Centers, the MACH, the Magnetic Fields, Atmospheres, and Connection to Habitability Science Center. And our goal is to see how magnetic fields constrain atmospheres on exoplanets. And our initial goal is to compare ionospheric escape from Mars, Venus, and Earth. This is a plot from one of my colleagues, Robin Ramstadt, that's currently under review for Space Science Reviews, that shows the magnetosphere of Earth, Mars, and Venus to scale, and shows the O plus outflow, the O plus on Earth, and the O plus and O2 plus from Mars and Venus to scale. And he's gone further. He's taken these data and integrated a net escape from Earth, Mars, and Venus as a function of solar wind dynamic pressure. So for Mars, Venus, and Earth, you see this interesting display. I'm not going to talk about it. I'm not going to steal Robin's thunder. This is a spectacular paper, and it should be out soon. And you, of course, can invite him to give a talk to explain how he got this spectacular result. So finally, let me close by telling you what I don't know and what I'd like to know about ion outflow. I'd like to see the chemistry associated with molecular ion formation and transport incorporated into a large-scale model and compared to the arrays observations of molecular ions at L of 5. Aurora are filamentary. Large-scale models of them are not, although the Glosser model is getting close. The filamentary nature was touched on last week by Herman Luhr, who talked about how the funny things that happened with filamentary field-aligned currents. Associated with this is, why aren't boundary coordinates in models? Now, 10 years ago, Tom Moore and I started a GEM focus group, and our line was, why isn't O plus in global models? And we were told by the then modelers that, well, that's too hard. Well, it isn't. They're doing it. And we have a bunch of very talented modelers, and I think that by the time they start putting a plasmasphere into their global models, that maybe they can used the boundary between the plasmasphere outer boundary and the polar cap boundary, which is the last closed field line. And they would indeed have boundary coordinates in their models and make comparison with the data that I showed here even better. And of course, I'd like to see the gap region sorted out. That's sort of the holy grail. People have proposed missions to send multiple satellites in there. I think there's still some out. Good luck. They're a hard sell, but maybe we can convince NASA that that's worth doing. And finally, of course, I think continued analysis of existing data is always a good thing. And with that, I think I'll close.
Okay, thank you, Bill. That was a very interesting and clear talk. We have a couple questions. And the first one is from Richard Denton. So he says, I thought that with the potential control, DE1 was supposed to be able to measure cold ions. Is not true?
Oh, yes, absolutely. It was true. There were two problems. One, the potential was bigger than they expected. And two, they couldn't run the instrument as long as they wanted. And they did get a set of data. I showed the RIMS data with the O+ shift. There is a set of data, but it's not synoptic as not as widespread as could have been.
Okay. And the other one is from Patricia Riff. I believe that you were showing, when you were showing the slide 15, she said, maybe the lack of correspondence means that they might have been accelerated below the observer. Is something related to slide 15?
To slide 15, let me go back to slide 15. How can I go back to slide 15? Are you seeing this?
We are seeing you.
You stopped sharing screen, Bill.
Oh, okay, well.
So she says it's the ion cyclotron waves.
Stop sharing the screen. Can you see this?
Yes.
So the question now is what?
The correspondence means that, like, about the ion cyclotron waves, the correspondence means that they might have been accelerated below the observer.
No, the conic angle puts a limit on that because you can plot the magnetic field strength falls off as a function of altitude. So if you look at the conic angle, you can put limits on how far below the satellite the energy was transferred to the ion distribution. And that was done here.
Okay.
So Angelopoulos really killed the resonance heating. Well, it's possible that there is resonance heating, but in the number of events that were captured by the burst mode on polar, none of them showed resonance heating. Now that could be because the burst mode was triggered only when there wasn't resonant heating. So there's wiggle room here, but the universal characteristic of resonance heating doesn't apply because there's cases where clearly it doesn't, and there's a large number of them that were detected by the survey that Angelopoulos did.
Okay. So also Sirivani Inturi says, if understand clearly, I observed that the energy and the concentration of ions in auroral zone is more during night. Why is more than in the day side?
Why? I don't understand the question. Could you clarify?
So he says that if he understands clearly, so the energy concentration of ions in the auroral zone is more during the night side, and why it's more in the night side than in the day side, if I understand well.
Can you see this slide?
Yes.
Is that what he's referring to?
Well, if he.
So this is the day side here for hydrogen and oxygen, and this is the night side. It looks to me like the day side and the night side are about the same for hydrogen, and there's more oxygen on the day side than the night side for oxygen. And this is consistent with data that's been published from DE and FAST. So I guess I don't understand the question about more ions on the night side.
So if you want to unmute and make a comment, yeah, we have time for that.
Is he referring to this?
We are waiting for his a number of which slide he's mentioned about. It's like 9 and 10. Yeah, those two, yeah.
Oh yeah, the comparison here is complicated, and there's a couple of things that are washed under the table. The polar and the DE data are not corrected for spacecraft potential. On polar, the spacecraft potential at perigee ranged from 5 to 15 volts positive. So this 15 volt lower limit floats around. It also floats around on DE1. The other thing that is under the table on this is the lowest energy channel is quite broad. It's like 50 or 60 volts. And where you calculate where you put the center of the energy to calculate the flux can affect the energies. So this comparison is qualitative. It's certainly not quantitative in determining what the actual distribution was. And the point I was trying to make in the following slides, and in particular this slide, is that there is a significant low energy ion population at the top of the gap region. And the Akebono and DE and the polar are teasing us about it, but we don't have a comprehensive view of what that energy is. One of the things that I talked to Alex Glosser about when we were when I was reviewing the paper and when we were going back and forth is using his data, using his model to calculate a energy over the full energy range of oxygen and hydrogen, and then going back and revisiting this analysis with the insights that come from his model. But so I hope that answers the question.
Okay, thank you. And there's a comment from Eric Lund says that the MACH et al. 1993 maybe showed that the connects fold up is lower than expected from the magnetic field strength. So it's a comment.
Yes, that's a paper that I published a long time ago, and our friend, our Japanese colleagues did. What you can do is you can plot the conic angle as a function of altitude, and then you can plot the magnetic field as a function of altitude. And you can show that if you start at any altitude, that the conic angle is always bigger than what would be suspected at that altitude. And what that tells you is that energy is being pumped into the ions perpendicular over an extended altitude range.
Okay, thank you. So if we have no more questions or comments, I would like to remind everyone that next week, next Monday on July 27, Dr. Wei Chao will give an overview of precipitation of energetic particles from the inner magnetosphere. So thank you, Bill. That was very interesting. Thank you very much. Very clear talk. Thank you, everyone, for attending this seminar. And yeah, if you have no questions, I look forward to see you all next week. Thank you.